All right, we're going to take a look at gas behavior today, and we are going to look at it really in much of today in the context of the mathematics behind gas behavior. So we've started simple, stuff you would have done in Chem 1. Now we're going to kind of move ahead a little bit. First of all, I want to just comment on some of the derivations of things that your chapter goes through. For example, it ends up giving you in your reading this formula of average translational energy is equal to 3RT over 2NA. And this is essentially the kinetic energy of molecules, and of course this is the gas law constant, this is the temperature, this is Avogadro's number, so 6.022 times 10 to the 23rd Avogadro's, yeah. But it takes you, and I think it's an interesting thing that really as you read through it, you should do it pen in hand. It takes you through, finding the pressure of molecules. It starts you off kind of with this formula for the pressure of molecules where, this capital N is the number of molecules and this is the mass of a molecule. This U, you could also almost substitute V in. This U is related to the speed or the velocity of a molecule. V is the volume that gas is inside of. So it's really related to the pressure, which remember is just how many times something hits the particular surface, is related to how many molecules, how big they are, how fast they're going, and in what volume they are. Because if it's in a small volume, it'll hit more often. If it's in a big volume, it'll hit less often. And so that's very much really what pressure is all about. But it takes you through this idea of pressure. It takes you into kind of looking at, we know kinetic energy, which they just call energy, is 1/2 mv squared, and taking a look at PV equals nRT, and doing a lot of substitutions from one to the other until eventually you get this particular formula. I would recommend take a pencil and try to follow along what they do. I don't need to regurgitate it here for you. But I want to just mention to you the importance of this particular equation here is that as we notice, 3 and R and 2 and Avogadro's number are all constant. So what this really tells us is that kinetic energy, which is our translational energy, is proportional to temperature, which is something that we have said and you've learned in Chem 1, and it also doesn't matter the identity of the gas. So those are some things that are actually true here. Doesn't matter what the gas is, the higher the temperature, the greater its energy will be. So I want to take a look at two graphs before we get into some more mathematics, and the mathematics will be related to these graphs. So I want you to consider graph 1, where in graph 1 this is going to be a graph of the number of molecules versus their speed. And this is just for a given sample of, we'll just make this hydrogen gas. And what we find is that at a given temperature, say here at 300 Kelvin, I want you to notice that even though kinetic energy, as we found, is proportional to temperature, at 300 Kelvin, and kinetic energy, of course, is the energy of motion. So it's very much related to our speed. Remember, kinetic energy is 1/2 mv squared. So kinetic energy, this is the velocity, and this is the mass of that molecule. So, there's a direct relationship between kinetic energy and speed, and it's related to temperature. But what I want you to see is that even at 300 Kelvin, they're not at all exactly the same speed. In fact, most molecules in here have a speed that's around in this range. But there's still molecules that are moving slowly. For example, they might have hit each other at that moment and are stopped. And there's some that, because of how they bounced off or whatever, are moving very quickly, and certainly some everywhere in between. So, you know, they're not all going a specific speed, but we certainly can see that most of them are falling kind of in an average range. Well, if we raise the temperature, what we see is that this curve will start to flatten out. It does not simply shift over, you know, because what that would mean is we wouldn't actually have any slow-moving molecules. But even though it's going faster, we still have some molecules moving slow, perhaps not as many anymore. And we certainly have more that are moving faster because they have more energy now. Their kinetic energy is higher, so in general their velocity is higher. So their average velocity is definitely higher. And if we cool it down, this curve moves over, and so that their average velocity is much lower now. But there's still some slow ones and still some fast ones. This distribution is known as the Maxwell-Boltzmann distribution. And he, you know, is showing that that graph does not simply shift over, it actually spreads out. I want you to compare that to a slightly different graph, and so this time we're going to maintain a constant temperature. We're going to maintain 25 degrees. Oh, I said this was a higher temperature, but let's just, so you know, you have it in your notes. That would be, for example, 700 Kelvin. This could be 100 Kelvin, so that you can see that as the temperature goes up, that curve spreads out. All right, so this one's going to be a constant temperature. And again, this is going to be the number of molecules and speed. And for this one, let's say that here's the curve for one gas, and this will be chlorine gas. Then I'm drawing very similar curves here. This middle curve is nitrogen gas. And the final curve is helium gas. And so we have a very similar distribution, but the difference here is chlorine has a mass of 71 grams per mole, or 71 AMU for a molecule. You know, nitrogen is 28 grams per mole. And helium is 4 grams per mole. So when we take a look at this, since we know that the kinetic energy is 1/2 mv squared, they're all have the same kinetic energy because the temperature is the same. But what's changing here is their masses are different. So the smaller the mass, the larger the kinetic energy. And so their speed actually goes up. Nitrogen, or if we look at chlorine, chlorine has a big mass. So its velocity, and I think I actually said that last one wrong, so let me restate this helium because I feel like that came out of my mouth wrong and I don't know what I said. So helium, I think I said their kinetic energy changed. It didn't change. Their kinetic energy stays the same because it's at the same temperature, but with a small mass, it's going to, if this is small, for helium, its velocity will be high. And we see that the average speed for helium is in this range. If we compare that to chlorine, which chlorine has a high mass because it's got that same kinetic energy because the temperature is the same, it's going to have a lower velocity. And so we can see that as reflected through its average speed here. And again, speed is related to kinetic energy. So if I said that wrong before, I apologize. I feel like that came out incorrectly. What I want to do is look at the mathematics now behind that and behind those graphs. And there's some wonderful mathematics, again, that are in your book that they take you through finding some of these various things. But I'm going to actually use two of the formulas that came up. The one is the first one I mentioned, that basically kinetic energy is equal to 3RT over 2 times Avogadro's number. And we also know that energy is equal to 1/2 mv squared. This is kinetic energy, which I'm going to write because your book uses, instead of v, u squared. that U is simply referring to velocity. So if you put these two equal to each other, so I'm just going to rewrite this one at the way your book does. E is equal to mu squared over 2. But if you put these two equal to each other and you rearrange it, you end up with an equation that looks like this. And again, if you want to see the very specifics of that rearrangement, it is in your textbook. It essentially takes into account the mass, which is the mass of an individual molecule in Avogadro's number, to account for the molar mass. So this mm here counts for molar mass. So what this is speed squared is equal to 3RT over the molar mass, which isn't particularly helpful. So we'll take the square root, and we get this equation. This velocity is often referred to as URMS, which stands for root mean squared velocity. You can see why it's root. Used to be squared, now it's the root of the square, so that's why it's called that. For us, this is important to us just as the average speed of a molecule. So we're going to call it that. Here's what I want us to take a look at is how we might plug those numbers in. So I'm going to just rewrite this again down here. And we need to look at units, we need to look at what we would plug in. As we look at this formula, if we would like to find this average molecular speed, we have to pick our R carefully. And in this case, we would like our R to be not the 0.008206.1, but the 8.314 joules per mole Kelvin form of the gas law. And I'll show you why in a moment that that's going to be helpful. Temperature is in Kelvin. We're talking gas laws. Molar mass kind of, normally is grams per mole, but in this particular case, this molar mass needs to be given in kilograms per mole. And here's why. A joule, just a little side note for you, a joule is a kilogram meter squared per second squared. So as we start looking at how we're going to get our joules to work out, we need this to be in kilograms. So I'm just going to show this to you with the units attached. So that's literally 3. That R, I'm going to, instead of plugging in joules, I'm going to plug this in. That's going to be kilogram meter squared per second squared times mole Kelvin, which was still part of that. That's literally the units of R, times the temperature, which is in Kelvin, divided by the molar mass in kilograms per mole. And when you look at what ends up happening, kilograms cancel, Kelvin cancels, moles cancel. Obviously the 3 will get multiplied out numerically, so I'm not going to worry about that. But we end up with the square root of meters squared per second squared, which would be meters per second, which makes sense for an average molecular speed here. So that's kind of how the units are going to work out. If we would like to find the speed of a given molecule, the average speed, that's what we'd look for. Now I'm going to derive 2 other equations for you related to that. So here's kind of my derivation. If, little side balloon here, sort of a central balloon, I guess. If I take 2 different molecular speeds, I'm going to call it speed 2 and speed 1, and I take one over the other. And that's going to be equal to temperature, because root mean square speed is equal to 3RT over the molar mass. But since I'm going to call this particular one speed 2, then it's a temperature 2 molar mass 2. And I'm going to divide it by root mean square speed 1, which is also 3RT, we'll call that temperature 1, over molar mass 1. Essentially, I just took one of those and divided it by the other. From there, we've got 2 different equations, and you're going to find some of these equations on your useless information sheet, so I suggest you check it to see which ones of these are present in order for you to use. So the first equation that becomes important, kind of scrolling back up here, is this one. This is an important equation. We'll call that equation 1. Now, we're going to do equations 2 and 3. So here is equation 2. If I am looking at the same gas, but at 2 different temperatures, then the molar mass is the same. And so the molar mass will end up canceling out. And what will actually, so will almost everything with the exception of this. The 3's cancel out, the R's cancel out, the molar masses cancel out, and so what we are left with is if you would like to compare, you have, for example, you know the speed of the molecule at one temperature, and you now raise the temperature, you could figure out what is the speed going to be at that new temperature. So that's going to be a useful equation for us. Another way we can use this kind of derivation up here is if we have 2 different gases. At the same temperature. So taking that same derivation, we can go ahead and if it's the same temperature, then the temperatures are the same, so they're going to cancel out of the equation. And so you end up with U2 over U1 is equal to the square root. Everything cancels except for these molar masses, which we don't want to leave that in that form. That's kind of an ugly form. So we're going to just rearrange this a little. Whoa, that didn't turn out. Square root of molar mass 1 over molar mass 2. And so this now is the equation that could be helpful. And it's helpful in the sense that if you know the speed of one gas, and now you want to know at that same temperature, what if I used a different gas with a different molar mass, you could figure out what the new speed of that molecule would be. And so that's going to be a helpful thing there. I'm going to stop this here, but tomorrow we're going to talk about how do these things relate to effusion, which you should have read about in your book, and we're also going to talk about something called the van der Waals equation, which is the correction for real gases. We mentioned real gases before. So that's where we're going to finish off tomorrow, and hopefully you took good notes on this, and we'll practice in class.